Hello guys, in this video I'm going to show you a tutorial on how to run a simple VHDL program or code on Vivado. And we're going to use here Vivado 2023, this version here as you see in the screen. This is the latest version you can find free on AMD or Xilinx website. Okay, so we have here our tutorial that we're going to follow. It has many steps. Very well explained. So we just follow the steps here for that tutorial. So first we open Vivado from the start menu. Okay, and after opening it, this welcome screen will appear, and from it we should choose create project. Here it is, create project. So, just to hint here, this is 2017. This manual is for 2017, but it can also apply for 2023. There is no much change. Okay, we should just press next. Here, we should choose a name and also a location for the tutorial. This is tutorial 4, as you know. So I already created a folder called tutorial 4. You can use the default location path or create a new path, whatever you like. And we're gonna name it VHDL or tutorial 4. Tutorial 4. Okay. Then we hit next. Step 4 here, select RTL project, which is already selected. It checks the option for don't specify source at this time. Don't specify source at this time. So we should check here the box, and it's already checked. And we click next. Step 5. So he's saying that we're gonna only simulate VHDL through Vivado. So as sentence explained, Vivado is a tool, software tool that simulate VHDL code for you. Of course, it's not like general simulation. It should be targeted to specific FPGA. Okay, so there are other tools that simulate VHDL codes or Verilog codes for general, like ASIC or FPGA, like Model Sim, for example. This is not Model Sim, but anyways. So for that purpose here, we have like some simple code that we're gonna see in a moment, and we're gonna simulate it in Vivado. So here we should choose the exact number of basically the platform on which we should download that code and run it as a circuit, build it as a circuit, which should be some FPGA. So since we will not do that anyways, with just simulation, not like real implementation, we're gonna choose some platform, which is the ones mentioned here, and we just gonna go with that. So we have here like many of them. So to filter out, so what you what you should do is just write XC 7 Z 0 1 0 C and LG 400. And as you see, we have like 3 platforms of 400. We just choose -1, which is this one here. Okay, and press next. Okay, step 6, click finish to accept the project settings. Okay, that's good. Wait a little bit. So in step 7 now, we need a new VHDL source. So basically we need like some text file to write our code in it. Okay, so under project manager, click add source. So here is the project manager, this window here on the far left. So under project manager, we click add source. We choose here in step 8, add or create design source. Okay. Then in step 9, we should create a file. So for the plus sign here, just click on it Three options will appear: add files, directories, create file. So we should create file because we don't have file in. If you have already a file that is you already wrote, you can choose it, but we don't have. Then this small window will appear for you. And just to be sure here, there are many languages actually to write basically, or to code basically hardware, okay, RTL. So one of the, maybe the most famous language is called the Verilog, okay? We're gonna use the older language, which is VHDL, okay? They are both like equivalent, they are doing the same thing, but of course they have differences, okay? And we should give some name to the file. Let's name it also tutorial 4, okay? And we press OK. Then we click finish, as step 11 here says. Okay, step 12, still set up the inputs and outputs as needed. So we have in our circuits that we have some equations that we're gonna implement basically. We have 4 inputs and 1 output. So the 4 inputs is A, B, C, D, and the output is called Z. So here we will define the inputs and the outputs. So the first is A, which is input, so you keep this one here. Second B is then C, then D, and then Z. And remember, Z is output. So you have here A, B, C, D, all are inputs, direction is input, and Z is output, okay? And each one of them is 1 bit. That's why you should not check the bus. If A is, for example, 8 bits, then we should, check this bus box. So just 1 bit, so we will not check it. We click OK. Then in step 13, double click on the file name in the source window. Here is the source window, sources basically. So we double click on the project. The project as a file name should appear under design sources. Here is design sources, but it's collapsed, so we should expand it. Here is the file, our file here. We double click on it. When you double click, it will open for you. It will open like a window in which you can code. You can write a code. And there are some code already there. Okay, let's explain it. You shouldn't care. This is like use IEEE dot standard logic 1164.all. It's like in or library IEEE, for example. You know, this is like in Python, for example. You might define some library, some library, and you hint or you point to a specific part of this library. Okay, so this is basically some, or for example, in C, sometimes we define a library. So for example, we say include standard input output.h, for example. So that's equivalent to that one, but for hardware. Okay, so we'll not touch that. Here, it based on our inputs, our definition, we define like 4 inputs, 1 output. It wrote that part for us. So that part is called entity, the entity part. In that entity part in VHDL, you define what's an input, what's an output. So as you see, A is input, IN, and it's of type standard logic. It's like you define a variable, something like that. You define a variable in C and give it a type. The type here is called the standard logic. Okay, that's an hardware type. Then the part in which you're gonna fill, it's called the architecture part, which is this part here, from that name or that line to that line. We're gonna put something. Basically, we're gonna put the description, the behavioral description of our circuit. Okay. So let's see our circuit. Our circuit is actually not there. We don't know the circuit, but we know the truth table, and that's a very powerful thing about using VHDL or Verilog or any hardware RTL language to describe a circuit, because you don't care about the logics, basically the AND or OR gates or any gates in the circuit. You just care about the functionality. And here is the functionality. The functionality is defined by the truth table. and here is our truth table. So what we're gonna do now is basically describe this truth table or convert this truth table into some code. Okay, this code will be can be understood by the compiler of VHDL and converted into a circuit on the FPGA. So let's do that. Okay, so what we're gonna do is basically write a code that describes this truth table. Let's see how. So first we should by looking here count the number of zeros on the number of ones. Okay, so looks like here the number of zeros is less than the number of ones. So we have here 16 cases in the truth table because we have 4 inputs and 2 to the power of 4 is 16. Okay, so we have this is number 0 number 1, 0 number 2, 3, 4, 5. So we have 5 zeros. So what we're gonna do, we're gonna do something like if else. Okay, so we're gonna define the 5 conditions like this. Let's assume we're gonna write it in Python or C++. I'm gonna say the following: if D equal to 0, and C equal to 0, and B equal to 0, and A equal to 1, then Z equal to 1. Else if D equal to 0, C equal to 1, B equal to 0, A equal to 0, then Z equal to 0. Else if D equal to 1, if C equal to 0, B equal to 0, A equal to 1, then Z equal to 0. Else if D equal to 1, C equal to 1, and B equal to 0, and A equal to 0, then Z equal to 0. Else if D equal to 1, and C equal to 1, and B equal to 0, and A equal to 1, then Z equal to 0. How about the other cases? The other cases are all 1s. So we're going to say else Z equal to 1. Okay? If you want to do it with the 1s, you're going to code like how many lines? You're going to write 11 lines because you have 11 ones in the output. But for the zeros, you have just 5. So it's easier. Both are equivalent, but it's easier. Less code if you do with the zeros. Okay? So that's what we're going to do. So again, we have in VHDL something like if statement. Okay? But to write this if statement, we have to do something called the process. Of course, as we go down in the course, we're going to know what this process means. But this process, basically, you can say it defines like a part of the code, part of the circuit. Remember, this will be converted as a circuit. It's not like normal programming languages. So process define a circuit, and this circuit has what's called the sensitivity list. So whenever one of this sensitivity list changes, basically it's an input. Whenever one of these inputs changes, then the behavior or basically the output of this circuit should change. Okay? So our process, our circuit basically is sensitive to its inputs, which is D, C, B, A. So when we define the process, we're gonna say process A, B, C, D. Okay, because the output changes, which is Z. It changes with any change in A, B, C, D. Okay. The beautiful thing about the process, it allows you to write if statement for some reason that we're gonna see in the course of, in the future, near future. Okay, so we're gonna write the process. Let's write this down here together. After begin and process, you might add this indent or whatever you like. If you wanna add this indent, I started like that, guys. Then I press tab. But this will make it more beautiful, that's it. But if you want to ignore the ending, it's up to you. It's okay. Then we write the sensitivity list here, A, B, C, D. We should write also begin. That's a new statement. Architecture here is a statement. It has a begin and it has an end. Process is also another statement. So it has a begin and it should have an end. So I'm going to put the end in advance. And yeah, end. Okay. Then in between the beginning and the end of the process, we should put the if statement. So I'm gonna write, as you see here, guys, it's very easy. if d equal to 0. Here is how we put like the input, if it's a condition, so you put always a quotation between around the value, okay, and because this is an AND gate, okay, and c equal to 0. This is the first statement, the first line in the second line of the truth table, or the first line that has z equal to 0, which is that one, the second one. D equal to 0 and C equal to 0 and B equal to 0 and A equal to 1. Okay, it has to be like that. And B equal to 0 again. And finally, A equal to 1. If all of this is satisfied, then we should write then here. Z, the output, equal to 0. And here is how we put so for inputs we put just like normal equation, normal equal sign. But for the outputs, we put it like that. It's like assign 0 to z. Okay, we're gonna also understand that in the future, so just forget this for a moment. This is the way we do the equal sign for the output, and this is the way we do the equal sign for the input. Okay, that's the first line in the truth table. Then we write else if, right? So else if, here is else if, just copy and paste them, because we do in all cases basically you have the same inputs and same output, and the output will be 0 all the time, but the input will change. So the second case here, second 0 0 1 0 0. So 0 in D, 1 in C, then 0 in B, and 0 in A. Then again, copy and paste. The third 0, that guy here, you have 1 0 0 1. So 1 in D, 0 in C, 0 in B, and 1 in A. Then the fourth 0, it is 1 1 0 0. 1 1, then 0 0. The fifth is 1 1 0 1. The fifth is 1 1 0, and then A is 1. Then you're gonna say else Z equal to 1. Okay, let's review together if we write it correct. So 0 1 0 0 1 1 1 0 0 1 1 1 0 1 0 1 1 0 1 0 1 1, 5 zeros basically, 5 zeros, 1 0 1 0 1 1 0 1 0 1. Okay, that's good, and that's the last case. Okay, now we should again, if a statement by itself is a statement, it's a statement. Any statement should end by end. So we should write end here, end if, I believe. Yes, end if. And for the process, we should also write end the process. And again, the indentation here, these spaces that I leave, it's optional, but it makes the code more beautiful. That's why I do it. Okay, step 25. If there is a syntax error, you will see the approximate space underlined in red. If you have, but thank God we don't have any syntax error here. He's saying if you have like some problem, you should see like a red line. Okay, so for example, we can create one and check that. Like for example, if we did like hen, not then, yeah, you see. That's good. Okay, click save again, Control S again. Okay. Now in step 26, he's saying that you can, or this tool can create for you a circuit, logic circuit, even before simulation. Okay. So to do that, you can view the schematic that was generated for you by clicking in Open Elaborated Design under RTL Analysis. Okay. So here is RTL analysis. This is on the far left here, and here is open elaborated design. So just click OK. Gonna take like a minute to generate the circuit for you. Okay, here is the circuit. Okay. So if you're interested, here, how the circuit is implemented. Basically, here it is. Okay. Step 27, since the syntax is correct, we can now write a simulation file to test our code. Basically, what simulation file means, you put some inputs and you look at the output. And of course, the output you should expect something. It's not random. So for example, in our case here, what we're gonna do, basically, we're gonna, the most intuitive input that you should do is basically the truth table itself. So you put 0, 0, 0, 4 zeros, and you should see 1 in the output. You put then 0, 0, 0, 1, and you should see 0 in the output, and so on. Okay. So there is a case here because you are spanning the whole truth table, which is 16 cases. There is a nice way to do that. Okay, I'm gonna see right now. Okay, so to do the simulation, we should do what's called run simulation. So in simulation here, here it is, on the far left. I believe right click or left click. Yeah, click on the run simulation and run behavioral simulation. This will open like a simulation window in which you're gonna see a signals, because remember, inputs and outputs is a digital circuit. So the inputs and the outputs are just signals. Okay, here it is. Here is the output menu basically, or output. The output signals will be shown here. Okay. Step 28, you may need to slide some window around to get okay. We did that. If you wanna take the maximum fitting, go to view and choose zoom fit. Okay. Can even do something like this. Step 29, click the restart button at the top of the simulation window. That's basically I'm not sure if it changes that. Let's check. No, it didn't change. Okay. So let's click restart here. Basically, it removes the default signals that you guys saw, a minute ago. So we start from scratch basically. Then click on A, B, C, any signal. Then right click and select force clock. What we're gonna do here, basically, we're gonna assign a clock signal to A. Okay, let's go to the truth table to see how we can span all the 16 cases. Okay, if we look at the clock signal for A, for example, it's like a clock signal 0, 1, 0, 1. It's a toggling all the time, right? It's like a clock. Clock 0, go up to 1, go back to 0, go up to 1, go back to 0, and go up, right? So that's what we're gonna do. We're gonna assign a simple signal, which is just a clock signal, to A with some frequency. Okay, so let's check what frequency he needs here. So right click, force clock, and choose binary here. Okay, and it's started by 0. Of course, the next edge will be 1. It will start at 0 nanosecond, and the period is 100 nanosecond. Okay, and the duty cycle, the duty cycle means what is the ratio between the high period and the total period. So 50% means the low is equal to the high. And click OK. That's A. Now for B, we're gonna do the same. Again, right click, force clock, binary. Again, start by 0, go to 1, start from 0 nanosecond, 50% duty cycle. But now for the frequency, it's gonna be half this frequency. 200. The first one was 100. And the press OK. Let's see why. Go back to the truth table. In the truth table here, if you look at A changes each line, right? 0, 1, 1, 0, 0, 1, 1, 0, and so on, right? B changes every 2 lines or every 2 rows. 0, 0, 1, 1, 0, 0, 1, 1, right? So if B is a signal, which and it is a signal, it should have a frequency half A, or it should have period double the period of A. Okay, that's why he make B, with double the period. Okay, for C it will be half B. The period will be half. I'm sorry, the frequency will be half B, or the period will be double B, and quadruple of A, right? Because it's 0, 0, 0, 0, 1, 1, 1, 1, and D would be the same. Okay, so if let's call the frequency of A is like let's call it 1000 hertz. Okay, so the frequency of B will be 500 megahertz. Then the frequency of C will be 250 megahertz. Then the frequency of D will be 125 megahertz. Okay, so if we start by 1000 megahertz here, 1 giga, this will be 500 mega, this will be 250 mega, this will be 125 megahertz. Okay, that's basically, how it goes. Or the period will be doubled or halved or doubled, I'm sorry, if you go from A to D. So let's see what he did for C. So for C, B is 200. For C, it will be should be 400. Yeah, 400 for C, and step 34 for D, it should be 800. So for C, force clock, binary, 0, then 1, start at 0, 57, and then here it should be 400 nanosecond. Okay. For D, force clock, binary, 0, then 1, start at 0, 50 percent due to cycle, and 800 nanosecond. Okay, that's it. So step 35, be sure to zoom still yeah, step 34. Yeah, in step 34, enter 800 nanosecond for D, and then click the run button. Okay, yeah, also yeah, so in step D again, put here 800. So the simulation time, we here set the total simulation time. So the total simulation time now is 800 nanoseconds. Okay. Then we press this button here, run, which runs only this button here, this arrow, this right arrow, which runs only according to the setup time for the simulation. So we're gonna just click, one click, and as you see, guys, 800 nanoseconds. Okay. So we need maybe fit. I'm not sure. Yes. Okay. Now we fit. Now there is a slider here, guys. You're gonna see at the end of the like the waveforms. Okay. Let's go back to the truth table here to verify that we are correct. Okay. The first case, 0, 0, 0, 0, we should see Z equal to 1. Look, 0, 0, 0, 0, and Z is equal to 1. Actually, whenever you move, these values here will change. Look, just look at this column. So if you go back, 4 zeros. If you go forward, A will be 1, right? If we go, and Z is 0 according to the table, which is correct. Then a third case, 0, 0, 1, 0. This is the third case, or 0, 0, 1, 0. Oh, yeah, because we should read from bottom to up, not from. So D here is below, right? So we should do like that. We should read like that, 0, 0, 1, 0. Let's see. Yeah, 0, 0, 1, 0. 0, 0, 1, 0. Okay. And the Z is 1. Okay. Now the fourth case is 0, 0, 1, 1. And we should have 1. Okay. Here is the fourth case, 0, 0, 1, 1. And the Z is 1. Fifth case is, let's check here, 0100. 0100. Okay, and Z is 0 as expected. Okay, 0100. Let's check the last case in all are ones. Here all are ones and Z is 1. Let's check the case before that. Case before last. In this case, we have 1, 1, 1, 0. 1 in D, 1 in C, 1 in B, 0 in A, and Z is 1. Okay, guys, that was it. That's basically the, you know, the lab. Okay, you should just need basically to take a screenshot of that window here. Okay, showing at least the last, any case. Just put this yellow bar at any case. Okay, and I'm gonna look at it and compare it to the correct answer in the truth table. I'm gonna also, of course, like check the 16 cases for you, but of course you shouldn't submit unless you are sure that the 16 cases is correct. Okay, you should like review them one by one. Okay, guys, thank you very much for watching and see you in another video. Bye bye.